All right, guys, this is lecture number 3 of our week 1. So we're chemistry 4, week 1, video number 3. All right, now at the end of the last video, I told you we'd be practicing something called the factor label method. And I told you that for the most part, I like to call it dimensional analysis, or start with what you're given, put it over 1, and then cancel units left to right. And you'll know what I mean by this in just a second. But let's start with the notes here at the top of page 1. Converting quantities from one unit to another. So we're not changing the value, we're just converting from one unit to another. By value, I mean like 12 inches is the same thing as 1 foot, right? We're not changing the value, we're not changing the distance, just the units that we're reporting it in. So I put down a little chart here, and you'll see this chart again. No need to memorize anything. The chart on the chart right now, the boxes that matter are the ones that say conversions. Mass conversions, length conversions, volume conversions. All right, let's do some examples. Write conversion factors for the following unit pairs. Liter and milliliter. Well, 1 liter is 1,000 milliliters. Grams and ounces. 28.3 grams is equal to 1 ounce. So I'm just using the table to get these conversion factors. Liter and quarts, 1 liter is 1.0567 quarts. And if you watch my fingers, I could have written those either way. Okay. Another example. Perform the following unit conversions. Now the last example we just did, we were just writing out conversion factors by looking at the table. This is the actual quote, start with what you're given, put it over 1, and move left to right, canceling units. So perform the following unit conversions. The first one, A, 16.0 ounces. We have to convert ounces into grams. I'm more concerned with looking at the units. So for unit conversions, in the bubble there, it says start with what you're given and put it over 1. That's what I'm going to do. 16.0 ounces over 1. That makes me realize in my head visually, oh, ounces is on top. Ounces will have to be on the bottom, and I write the conversion factor 28.3 grams for every 1 ounce. Cancel the ounces, I'm left with 453 grams. 2,500 milliliters to liters, start with what you're given, put over 1. 2,500 milliliters over 1 times 1 liter over 1,000 milliliters. My milliliters cancel, looks like I forgot to cross them off, but milliliters cancel, and I have 2.5 liters. C, 99.0 liters. 99.0 liters over 1. Start with what you're given, put it over 1. For every 1 liter, on the bottom, there is 1.0567 quarts on top, 105 quarts. Okay, now you've just done dimensional analysis 3 times. The number of significant figures I started with, by the way, is the number of significant figures I report my answer in. Next example. Convert 0.840 quarts to milliliters. Same type of problem. Start with what you're given, put it over 1. 0.840 quarts over 1. I use the table. I got to get rid of quarts. So I put 1.0567 quarts on the bottom for every 1 liter. Now I'm in liters. Cancel liters. On the bottom, for every 1,000 milliliters, there's 1 liter. Started with 3 significant figures, 0.840. My answer has 3 sig figs, 795 milliliters. Why is that? Well, conversion factors are, we take them to be exact or true. So 1 liter equals 1,000 milliliters. That is an exact number, kind of like a counting number. So it's infinite sig figs. We start with 3 sig figs in that example. My answer is 3 sig figs. Okay? More examples. This one's a little more difficult, but it's still dimensional analysis. 1 nautical mile, 1 nm for nautical mile, is equal to 6,076.1155 feet. All right, so that is a conversion factor. 1 knot is equal to 1 nautical mile per hour. These are given to us. Here's the question that the problem is asking. What's the speed of a boat? And they want the boat's speed to be in meters per second. What's the speed of a boat going 4.3 knots? All right, well, what are we going to do here? We're given a lot of numbers. 14.3 knots is equal to 14.3 nautical miles per hour. And I figured that out from the what was given, where it says 1 knot is the same thing as 1 nm, or nautical mile per hour. So I make that my start with what I'm given, but you never want to write a slash in these things, because the slash is the horizontal line. So 14.3 nautical miles all over 1 hour on the bottom. Now I can get rid of hours first or nautical miles first. I'm going to get rid of nautical miles and get that into meters. So 6,076.1155 feet for every 1 nautical mile cancels my nautical mile unit. And then for every 3 feet on the bottom, there's 1 yard. I'm out of feet. For every 1.0936 yards, there are 1 meter. And I'm out of yards and into meters. I'm going to stay with meters there. That's why I've circled the unit. It's the one I want. And then I got to get out of hours now, which is all the way on the bottom left. So for every 1 hour on top, there's 60 minutes. Cancels my original hour. I'm in per minutes. For every 1 minute, there's 60 seconds. You do all the math. You multiply all the top ones, divide by all the bottom ones, and you end up with 7.36 meters per second. So if that was too fast for you, back up, write these notes like you're supposed to, practice it, and see that you get the same answer, 7.36. All right, measuring temperature. The measure of how hot or cold an object is. That's what temperature is. Temperature's definition is the measure of how hot or cold an object is. The SI unit for temperature is kelvins, and the degrees Celsius, if you just take whatever degrees Celsius you have and add 273 to it, that's how you get degrees Kelvin. So that box right there is how you go from degrees Celsius to degrees Kelvin. All right, in a second we're going to learn how to go from degrees Fahrenheit to degrees Celsius. Absolute zero, by the way, is 0 Kelvin, or negative 273 Celsius. That's the value where molecules in a solid even stop vibrating. So absolute zero, absolute no movement. Now, how do we convert between Fahrenheit and Celsius? At the bottom of the last page, we saw the equation Celsius plus 273 gave us Kelvin, but how do we go from Fahrenheit to Celsius? Well, the equation is degrees Fahrenheit is equal to 9/5 times the degrees Celsius value, and then plus 32. So here's a question. What's 136 degrees Fahrenheit in Celsius? Well, we write down our equation, especially on my types of exams, because you want to write down anything you can to get partial credit. So we then plug in degrees Fahrenheit is 136 equals 9/5 times my unknown degrees Celsius plus 32. 104 equals 9/5 degrees Celsius. So your degrees Celsius, if you do the math, is 57.8 degrees Celsius. All right. So energy and heat. Heat is closely related to temperature, but temperature is just a measure of how hot or how cold something is. Heat, on the other hand, has a direction, a movement of energy. So let's get to the notes here. It says, all chemical reactions are accompanied by a change in energy. Energy is defined as the capacity to do work or supply heat. So energy can actually do work or supply heat. So in this instance, I'm talking about energy in the form of heat, supplying heat. There are 2 kinds of energy, by the way. You may have heard of them. The first one is potential energy. This is stored energy. Examples of potential energy, I'll give you several. A rock on the top of a hill certainly has a lot of potential energy. Another example, a coiled spring. That's if you take a spring and like you push it. So it's like a wound up or a coiled spring. It has a lot of potential energy. Water behind a dam, potential energy example. So you get the idea. The energy is being stored. It's ready to just burst out into kinetic energy. Kinetic energy is number 2. Kinetic energy is the energy of motion. So potential energy, stored energy. Kinetic energy, energy of motion. Now, potential energy and kinetic energy are interchangeable, right? I can push that rock down the hill, the spring can uncoil, and I can lower the dam to release all the water. Now, in chemical reactions, stored energy, or potential energy, in the reacting compounds, that can get converted into heat. All right? Now, heat, I'm finally going to define heat for you. Recognize that its definition is different than temperatures. Heat is the kinetic energy of moving particles, all right? And these particles are moving, and they're moving in one direction or another. Now, the SI unit for energy is something called the joule, okay? Joule, capital J, but the metric unit is often used quite a bit as well, and that is the calorie, C-A-L-O-R-I-E, abbreviated CAL. All right, it's a conversion factor here is 1 calorie is equal to 4.184 joules. So that's taken to be exact. Okay, that's an exact number. All conversion factors are exact numbers. So 1 calorie is equal to the amount of heat required to raise the temperature of a substance by 1 degree Celsius. I'm sorry, the amount of heat required to raise the temperature of 1 gram, and it's not just any substance, it's 1 gram of water by 1 degree Celsius, my bad. So 1 calorie, just to reiterate, 1 calorie is equal to the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And that's also equal to 4.184 joules. Now, not all substances, water, for example, versus copper versus iron, have their temperatures raised to the same extent when equal amounts of heat are applied. For example, if I boil water on a stove, right, the pan gets a lot hotter, a lot quicker than the water that's being boiled, right? As you warm up the heat, the pot gets hot real quick, but the water doesn't. Water is really good at being what's known as a coolant, and we'll get that. We may get back to that in a bit. But first things first, let's stick to our notes here so I don't get off topic. Not all substances have their temperatures raised to the same extent when equal amounts of heat are added. Next bullet point. The amount of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius or Kelvin is that substance's specific heat capacity. Specific heat capacity has units of joules per gram per Celsius. For aluminum, specific heat capacity is 0.897 joules per gram per degree Celsius. That means it takes 0.897 joules of energy to raise 1 gram of aluminum by 1 degree Celsius. Copper is 0.385, doesn't take as much heat. Copper gets hotter quicker. Iron, 0.452 joules per gram per Celsius. Now look at water, way, way, way bigger, 4.184 joules per gram per degree Celsius. So metals, aluminum, copper, and iron, they don't require as much heat to raise the temperature of 1 gram by 1 degree Celsius. As a result, they get hotter quicker. Okay? Water requires a lot of heat. It can take in a lot of heat before it raises its temperature by 1 degree for 1 gram of water. All right, so let's take that further and put it into an equation for heat gain or heat loss by a substance. Okay? So heat gain or heat loss is measured in joules. That's why you see the capital J in parentheses. And that is equal to, the heat gain or lost by a substance is equal to the mass of that substance in grams times that substance's specific heat capacity in joules per gram per Celsius times the temperature change. Now the temperature change is the final temperature, TF, minus the initial temperature, TI. So we have an equation here, right? Now I've put in words here, but the equation drills down into something very, very simple. Q equals MC delta T. Q equals MCAT, right? Try to remember that. Q equals MCAT. So what's the specific heat of aluminum? This is an example. What's the specific heat of aluminum if it takes 161 calories to raise the temperature of a 75 gram sample of aluminum from 12 degrees Celsius to 22 degrees Celsius. So we have 161 calories is required to raise the temperature of a 75 gram sample from 12 degrees to 22. So Q equals MCAT. Q equals MC delta T. In other words, Q equals MC times TF minus TI. Let's just plug numbers in. If it's one equation, we should be down to one unknown in order for us to solve it. 161 calories equals 75 grams times C, our unknown, our specific heat. Specific heat's the same thing as specific heat capacity, times 22 minus 12. So when you do the math here, you get a specific heat for aluminum of 0.21 calories per gram per degree Celsius. Not joules in this instance because they gave us the heat in calories instead of joules. All right, top of this page of notes, we're moving on to something totally different. So if that was too fast or if that was confusing, you can always rewind this video and rewatch it over and over. And you're supposed to rewrite your notes too, right? So as you rewrite your notes, you might find questions. You can leave comments below, I'll reply, or you can send me a private message if you'd like as well. Either in Canvas, on YouTube, by email, either way. Density. Density is equal to the mass of something divided by its volume. So density is mass over volume, and the mass is in grams, and the volume depends on what it is you're talking about. For solids, density is expressed in grams per centimeters cubed. For liquids, we report density in grams per milliliters. And for gases, because gases are so voluminous, they take up so much space, generally speaking, relative to solids and liquids. Solids and liquids are condensed. Gases are not. So we report these guys in grams per liter. All right. So that's the end of week 1 of our notes for Chemistry 4. You have everything you need. 3 videos for week 1 Chemistry 4, and you can now use these 3 videos. You want to rewrite them all on your own lab notebook, or just any type of white paper. Write them yourselves with a pen, and then rewrite them and read them and make sense. Writing things down is how you retain the information, okay? And then you can use this information for your homework, and of course it's going to be on the quizzes and exams. All right, so I'll see you next week.